functions. And special functions for us will come in two categories. They'll come in this goofball category. So special functions and the reason to pick these is they're important, you know, in the magisteria of physics. The beta and gamma functions are much less important than, for instance, Bessel functions. But by picking a couple of these integral and differential equations, solutions to each of these, you basically understand the techniques to deal with any other new ones that you'll encounter in your life. So we'll start with these, and we'll really just do two. So we'll do the gamma function and the beta function, really creative names. And somewhat annoyingly, gamma shows up a lot in physics and math. So you got to be a little careful about what you're calling the gamma function. But here it is. So let me just say this is important. You'll see it in probability, pure probability theory, and you'll see it in thermodynamics, therefore. But let me just ask like kind of a goofy question. Okay, let me even start before that. Do you guys know what that is?
Factorial?
Yeah, right. So specifically, what's that?
Like 4 times 2 times 3 times 1.
Great. Which is 24, is that right? Yeah. Okay, what's this? Do you think it should exist? Why or why not?
Probably not, because the factorial, like, I don't know if it's a function. It's definitely not continuous. It only takes like integers as inputs, so I don't know.
Yeah, so far as you guys have seen this defined is you only put integers into the factorial, right? So this should not be okay. So what on earth is this? And I don't want to use the exclamation point because now that's kind of a reserved symbol in this class. Also, I could ask, so we'll call this question 1. I could ask question 2, which is equally bizarre. What is this? 3/4 factorial, right? So maybe same objection is we define this on integers, and then we have the definition that 0 factorial is actually, what is 0 factorial? You guys remember?
It's 1.
Yeah, 0 factorial is defined to be 1. You'll see why that's not actually a definition. But let me kind of bring up this graph. It was smart enough to have it up. Yeah, cool. Can you guys see the Mathematico window?
Yeah.
Yeah, perfect. So let me just list plot factorial. Could you guys imagine there being like a smooth curve interpolated through these? Something that looks like maybe even super exponential or exponential. It turns out that there is such a thing, that you can define a continuous function of a continuous variable x. X, you know, with a lot of exceptions, goes in between negative infinity and infinity. That smoothly goes through these points. And you could define, for instance, what 3/4 factorial is, and you could define the derivative of this. This is what the gamma function is. So this is the gamma function, and you can see that it kind of returns a thing that looks right. Let me see if I can get those both in screen. So you can look at the y ranges, goes to 120 and 120. So that's 5 factorial. And already there's something kind of weird because gamma 6 looks like it's 5 factorial. And then, so essentially our job is extend factorial to the entire real line. It turns out we get something else that we won't talk about in this class, is the gamma function actually extends into the complex plane. So this is the argument. So if you remember, the argument of a complex number is the phase in polar form. So z, a complex number. So this is it in rectangular form, a plus ib. And you could imagine that in polar form, r e to the I theta. So this is like a color-coded plot of theta. And along this axis, the real line, it's real. And then we have some goofy stuff happening here, 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 and here. So this is useful in pure math, and it's useful, therefore, in certain types of physics. So let me just integrate something. So I'm going to integrate sine x divided by x to the 1.2. And what you'll see is something shows up, and Mathematica recognizes this integral as a gamma function. So gamma function, the extension of factorial, is useful. And let me, before we leave here, because I think it's just like right on the graph, what do you guys think these like weird white dots where the phase goes crazy? Like the phase seems to go from 0 to 2 pi all at one point, and then the thing itself goes white, so it goes crazy. Any guesses about what that is? So let me just, whoops, plot range all is a bad idea here. So we just change this from plotting 1 to 6 of the gamma function to 0 to 6, and you'll see, wait, something crazy is happening. Is 0 factorial really 1? Well, we'll go back and investigate that. Okay, so this is our new friend, the gamma function, and it's going to have another friend, the so-called beta function. And the beta function is just kind of a derivative of the gamma. And again, part of this is just as an excuse to talk about integral equations. Okay, so there it is. And without further ado, we'll define the gamma function. We will define, and this is Euler's form of the gamma function. And for now, we'll just keep it real. But actually, let me do that. We'll keep it real, but I'm going to call this z anyway. So until you realize it doesn't matter, you can think about z as a real number. And we have a dummy variable inside of this integral equation that we're going to integrate out and over. Okay, so this is the definition of the gamma function, or at least our definition. And what needs to be true, just putting this there at the outset, is the real part of z needs to be greater than 0. And what this is going to turn out to be useful for, at least at first, is that gamma of z plus 1 is equal to z factorial. So for example, gamma of 5 is going to be equal to 4 factorial, or 24. But gamma of, pi, for instance, exists. So now the next time you see pi factorial, you can say, like, I could figure that out by going to Mathematica. Any guesses about how we might prove this? Because we're going to prove this. This is one of the 2 useful techniques that we're going to go over with integral equations and proving stuff in general. If you ever had to code up something that returned a factorial in a programming class, what technique would you use?
Some kind of iterative process.
Yeah, and the best one to use, usually when people are teaching folks about recursion, functions that call themselves, which is pretty cool, you can do that. So recursion or iteration is how I would program a factorial. It turns out that that makes it a wonderful candidate for proof by induction. Has anybody, well, so we'll say it this way. If you've seen and are comfortable with proof by induction, indicate yes somehow on Zoom. And if everybody is, we won't go through it. I doubt that's the case, so we'll probably go through it. Okay, that's a resounding go through proof by induction. So this is our claim that for the integers, this integral equation, gamma of z gives us gamma of z plus 1 equals z factorial. So gamma of 6 would be 5 factorial, for instance. So that's our claim. And our proof is going to be proof by induction. Does anybody know kind of like the broad strokes description of what proof by induction is? Okay, so this will be a nice little aside. I think there's like a shape that I could use for this. Okay, so let's say I have a whole bunch of dominoes in a line. Dot, 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 dot. And I make the following two claims. So I say the following two things are true, is that the first domino falls, and then two, the kth domino knocks over the one to its right. What have I just proven? Which is really not the way that you would want to prove this. This would be more of a fun experiment than a theoretical proof. So I can prove that the first domino falls over, and I can prove that the kth domino knocks over the k plus 1th domino. What have I proven about this entire setup of dominoes?
They're all going to knock each other over.
Exactly. So this is the logic behind a proof by induction. So you prove a base case. We're actually going to do two base cases because the whole 0 factorial thing. It's kind of circular to say that, well, it's treated separately when you guys learned about it. So we'll do 0 factorial and 1 factorial. So if we prove a so-called base case, and then we prove that k implies k plus 1, what we've done is we've proved that all of the cases are true. So if the 0 case is true, and if each case implies the next case above it is true, then we've got them all. So it's like knocking down dominoes. This is what's called the base case. And this is not the world's best example of, first example of proof by induction, because 0 factorial is a little bit weird, but it's good enough. And this is where it shows up for us. And this is what's called the inductive step. Okay, and again, in real life, you would just probably hit the dominoes, but we're theorists in this class. Okay, so how that would work for us is in general, you'll only have one base case. Again, 0 factorial is so weird, and seeing these techniques multiple times is good. So our base case would be show that gamma, as defined with that equation, is equal to 0 factorial, which is equal to 1. And again, if that didn't happen, we wouldn't despair. We'd just say, like, you came up with some weird definition for the integers, and we could still show that this is true. This claim is true for, integers 1 through infinity. Okay, so let's just write down what the thing is. So by definition, gamma of 1 is integral over the positive real line over this dummy variable t of that. But then z is 1, so I will turn this into 1, which means the whole integrand is t to the 0, so that's 1. So base cases are always really nice. So that's integral from 0 to infinity. T to the 0, 1 minus 1, that's 1. So this is integral e to the minus t dt. I can do that. So that's e to the minus e minus t evaluated at infinity and 0, which is equal to 0 minus minus 1 or plus 1. So that's our base case, doing good. Okay, so I will give you guys base case number 2, which is show that gamma of 2 is equal to 1 factorial, which is also equal to 1. And this is the one that we kind of really need, actually. So gamma of 2, if this formula gets everything right, would be 2 minus 1 factorial, or 1 factorial, which should be equal to 1. So I'll give you guys 5 minutes to do that. So hopefully everybody at least got to the point where they recognize the technique that you would need to finish this. So I'll use it a couple of times yet. Or did somebody actually finish proving it? That'd be good. That's like quick work with the integral techniques, if so. Okay, so let's just write down what this is by definition. Integral over the positive real line, e to the minus t, t to the z, which is 2, minus 1, so t to the first power, or just t, dt. And then I just have integral t e to the minus t, and there's a reason to rewrite it like that. So I'm stuck with something that would disappear if I took its derivative, and something that would never disappear no matter how many derivatives I take, but has a pretty easy integral. What technique should I use to integrate this? Because I don't know what integral t e to the minus t is offhand. This is a great candidate for what?
Use integration by parts.
Exactly. So we'll integrate this by parts, and we'll put a little dictionary over here to do that. And I have integral u dv is uv evaluated at the limits minus integral of v du. Okay, so the left-hand side is the thing that I would like to integrate, and the right-hand side is something that I could actually integrate, or in this case, evaluate. So u does not get integrated. I see u itself, and I see du here. So u is the thing that we're going to choose. What are we going to choose for u? The thing that we'd like to derivative and get rid of.
Definitely just the t, not the exponent.
Yeah. So the wisdom of using this is knowing what you want to get rid of and know what you don't mind taking integrals of at all. In this case, v, I'm going to still have to take an integral of. So that would be the e to the t. So choosing u as t and choosing v as everything left over. So that's e to the minus t. That gives me that du is equal to dt. That's great. And then dv is equal to minus, because we're taking a derivative, e to the minus t dt. So then you could also do that backwards. So you could actually, because we're going to substitute this in, I'll put the minus sign there and there. So I think the more traditional way of identifying this stuff is you're picking out everything on the left-hand side. So u is equal to t, and then the leftovers got to be dv. So I think that's probably the more sensible way of explaining it. So e to the minus t dt is everything that's left over. now UdV is this thing, this, which means V is this integrated, which is minus e to the minus t. So probably a little bit more clear to do it that way. Okay, now just plugging in, we have, this is UV by choice. So this equals UV evaluated at the endpoints. So UV, that's TE to the minus t with another minus evaluated at infinity and 0. So that's this term. And then the minus integral v du term, minus integral, same limits, v du, v is minus e to the minus t, and then du is dt, so that's nice. Okay, so this I'm just gonna leave and we can argue about it in a second. And then minus minus gives me a plus, but then I integrate this, so I get another minus. So I end up with so minus 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 e to the minus t, which looks familiar. And again, this is all equal to the gamma function evaluated at 2. Okay, what's the first term? What does this turn into?
Turns into positive 1. At least when
Why?
I did it. So the way I separated it into 2 limits and then used L'Hopital's. And the first limit has e approaching infinity on the bottom, so it goes to 0. And then the second limit has e approaching 0 in the denominator. So that one approaches 1, or -1, but there's a negative in front of it, so it's positive.
Great. So everything you said is right with one exception, is that e to the thing in the denominator, the e to the t, when you evaluate e to the t at 0, it's not 0, it's 1.
Right. But there's a 1 on top, right? So
the L'Hopital for the first term with the infinity, great. The other way of thinking about it is that t goes to infinity slower than, this is the physicist way of explaining it. T goes to infinity slower than e to the t, the exponential. So in all cases, this is this, right? So at infinity, the exponential is going to win. So this is going to be equal to 0. And then the second term, you have 0 on top, but then you have e to the 0, which is 1 on the bottom.
okay, that makes sense.
Yeah, so everything you said was right with the exception of just the thing that you evaluate on the denominator in the second term is 0, not 1. So yeah, not obvious, but that's actually, it's a really hard fought 0. So that's 0. And then this we evaluated in the last one. So this is literally this term. So this is minus minus 1 or plus 1. So we got a goofy term out front from the so-called surface term of the integral by parts. And then the second thing is exactly what we evaluated for gamma 1, which is, you know, after you've done a few of these, this is when you start to get suspicious that proof by induction works, is you keep seeing the same term show up. Okay, so that was work. That was just the base case. So now to do a full proof by induction, we need to also do the inductive case. And what the inductive case is I got to show that if k is true, that implies k plus 1 is true. So this is the important part where we've shown the first domino falls. The inductive case is showing that the kth domino knocks over the k plus 1th domino. So that's what's called the inductive step. So that's showing that gamma of z plus 1 is equal to z factorial. But what I'm really going to do is write that z times z minus 1 factorial. So that's just what factorials do. Or z times gamma function of z. So this is really what we want. So this is the inductive step, because that's what a factorial is that the factorial of n plus 1 is n plus 1 times n factorial, just multiply by the next term. So gamma of z plus 1 equals z times gamma of z, and that would be my inductive step. Okay, so like with basically everything in math physics, you know, sometimes higher level math classes turn people off because there's like some proving and inspiration in there. I know I hated analysis because just, I don't know, I thought I would come up with like perfect proofs and then the grader would be like, you gilded the lily or some weird cryptic comment and then give me 0 points. Math physics usually 99% of the time, just like write the thing down and wade right in. So this by definition is gamma of z plus 1, right? So we just put z into the integral equation. And then do the plus 1 and minus 1. Okay, with the assurance that I am not going to make you do this, tell me how, if I were to send this to like, you know, some Soviet prison camp where they have a bunch of PhD mathematicians and make them do this proof, how would they evaluate the next step of this? So I have an integral that looks like integral from 0 to infinity e to the t, which I can integrate pretty easily, times t to the zth power. What would I do? I would just have to do it z times.
Same as before, the integration by parts.
Yes, so this is integrate by parts. If I were to get it down to a final tractable form, I would have to do it, you know, z times. But we won't do that. We will just do it once, and then everything that we need will fall out of this. So integrate by parts again. So what I will ask you guys to do, because this is really good practice, fill out the integrate by parts table. What would u be equal to? What would the leftover dv therefore be equal to? And then what would that imply about du and v? So what should I choose for u in this case? Remembering that I won't actually make you guys do it.
It would still be the t to the z power.
Yeah, so now it's just the t to the z term. And then this is, you know, if you recognize it right here, excellent job, is we take du, the derivative of that, that's z comes down because we're taking a derivative with respect to t, right? So that's our variable of interest. And then all of a sudden that z is exactly what we're looking for. So that turns out to be that z, and that's kind of it. And then what would dv therefore be? Just the leftovers. And then minus e to the minus t. Okay, so writing that out after the integration by parts, we would end up with this surface term, minus e to the minus t, evaluate, times t to the z, evaluated at infinity and 0, minus integral from 0 to infinity, another minus e to the minus t, and then z times t to the z minus 1 dt. Okay, and we've been through this argument before. You can L'Hopital it at 0, or you can do the physics hand wavy BS and say that the exponential. So if you think about the series expansion of an exponential, there's for every n you can think of, there's a t to the n term. So the exponential always grows faster than any polynomial. So it's going to win at infinity. And then at 0, the numerator is 0 or the denominator is 1. So same argument, except instead of, like we said here, e to the t grows faster than just t to the first power, it grows faster than e to the zth power too. So that's equal to 0. And then we're left with this. Let me make some room for this. We have, okay, I got the minus minus, whatever. Our variable of integration is t. So this z is just a number. You know, it's a parameter, but it's something that we're not integrating over. So I can just pull it out of the integral, and then we get a minus and a minus. So that's z e to the, or integral from 0 to infinity. And then I'll just dress it up so it looks, yeah, exactly the way that we presented the other ones. E to the minus t, t to the z minus 1 dt. And this is gamma of z, right? So that's the definition, our original definition of what gamma of z is. So truly this is z gamma z, which is exactly what we wanted. So honestly, it wasn't that bad. So a little bit of heavy lifting with realizing that you needed to, you know, use integration by parts, and you needed to use integration by parts even when it wouldn't give you an answer. It would just pull out, you know, the correct factor. But so this is it. And the thing is nothing about any of this, neither the definition of the gamma function nor the proof that we just finished, has anything to do with z being a whole number. So z could be, you know, 1/2, z could be pi. There will be places where the integral blows up. We'll come back to that, but just realize we didn't put any special restriction on z being a positive integer. So that's pretty great. So any questions about that before we start trying to use this? Okay. So, so the first thing we know is that kappa gamma. So we'll say restricted. Is that, again, all that stuff that you know about the factorial function is true, but now we can extend it and define factorial for, you know, whatever positive. So one of the restrictions is that gamma of 0, which would be -1 factorial, doesn't exist, which, you know, shouldn't be too groundbreaking and surprising. What we can do is this. We can find gamma of 1/2 and gamma of -1/2. So those are negative and fractional values. Okay, before we wade into finding what gamma of 1/2 is, so let me set you guys on the path to not doing a lot of work and saving time and energy right at the outset. So if I knew gamma of 1/2, what is gamma of -1/2? Which is to say, can you express gamma function of -1/2 in terms of gamma 1/2? So what is the one thing that you know about the gamma function? And that was kind of our step, our inductive step.
That gamma of z is z times gamma plus 1.
Yes. So gamma of z plus 1, I'll just say it exactly backwards from you,
Oh,
the
yeah.
way you said it, because we have the bigger thing on the left-hand side. But yeah, so gamma of z plus 1 is equal to z times gamma of z, which, well, what's true about gamma or 1/2 and negative 1/2? Well, 1/2 is negative 1/2 plus 1. And just substituting in the fact that z is the thing that we want, gamma of z is negative 1/2. If I knew gamma of 1/2, I could just use this. Or, you know, in the most directly useful way of doing it, minus 2 times gamma of 1/2 is equal to gamma of minus 1/2. Okay, do you see how this is in a way infinitely useful? Let's say that I wanted to then know gamma of negative 3/2. What could I then do? And you don't have to say the specific thing. It's just, you know, kind of holistically, if I knew gamma of 1/2 and I use that to find gamma of negative 1/2, what could I use to find gamma of negative 3/2?
You could use gamma of negative 1/2.
Yeah, what could I use if I wanted to find gamma of negative 5/2 or negative 7/2? So you get the idea, is that anytime you work hard to find any value of the gamma function, in the same way that the factorial of 1 tells you the factorial of all integers, if you do a little bit more work, namely multiply by the next integer value, same thing is true for the gamma function. You just multiply, you know, if you know some value, you know all of the integer spaced values from that, even if the original value itself is a fraction. So on the quiz that we'll have on this, remember is that, you know, you might not have to evaluate this thing from first principles. If you know any value that's any number of integers away from the one you want, all you have to do is the same thing you would do with a factorial. The problem is we don't know gamma of 1/2. And the integral that you have to do to find gamma of 1/2, hardest one we'll do today, is kind of important. So it's worth doing. So this is really great. It seems like we're going to be skipping a lot of work, right? So that's true. But the problem is what is gamma of 1/2? So you guys should write down the integral form of that and then realize, like, you know, our trick doesn't quite work anymore. So gamma of 1/2 would be integral over the positive real line, as always, e to the minus t, and then t to the 1/2 minus 1 dt. Or, because radicals look really gross, I'll write it in the grossest way possible. Yuck, right? So I imagine that you guys probably never even saw that in integral calc. So that's actually not a great form. Okay, does anybody have a suggestion about how you would try to evaluate this? What's the problem with integration by parts? I can't derivative this away. Right? I can't derivative a negative square root away. It's going to turn into negative 3/2 power, negative 5/2 power. It's never going to disappear. So what's another thing that we could maybe try to do? It's probably the first big class of tricks that you guys learned for doing ugly calculus stuff.
Some kind of like substitution.
Yes. So we'd like to substitute in some new variable that just makes it look nicer, and then hopefully everything works out. Just to kind of get to the point is we don't want the square root. So let's just say, well, let's define y to be equal to the square root of t. And then y squared would be equal to t, and dt, which is the thing we have, would be equal to 2y dy. So that's our dictionary for a change of variables. And how this works in real life is, you just kind of go fishing until you find something that kind of works. Okay, so say again? Yeah.
How is that different from U subs?
It isn't. So U sub is just a change of variables, but in kind of calc teacher colloquial discussion, they always use U, so they say U sub. Yeah, you could just make the Y U, and that's exactly the same thing. So just generically a change of variables. Yeah, good. Other questions? Okay, no suspense. I chose this because it works. Putting this stuff in, so this becomes 1 over y e to the minus y squared. And then, holy cats, dt becomes 2y dy. And then y upstairs, y downstairs, everything nice happens. Okay, so it looks like we made progress, sort of. So this becomes 2y e to the y squared dy. If you've taken a stats class, you know this is like the error function, and it actually equals to the square root of pi over 2. I will really quickly go through the normal distribution integration trick. So this is a standard deviation, right? This is a bell curve now. So this is basically an unnormalized, but half of a bell curve. This is how that integral is done. So maybe today's lesson is really just like the grab bag of 5 integral tricks that physicists use 90% of the time. So we want the number that is equal to this. And in our particular integral, for our U sub or change of variables, there's a 2 in front. But this is the active ingredient. So we want this. The trick goes like this, is do something that makes it look like you're about to do a lot more work than you need to do. Right? So is it clear that that's true? I just took a different copy of this number alpha, but I'm integrating over a different dummy variable. Why would I ever want to do that? Well, so I can combine these. To get that. What am I integrating over? And what would maybe be a better coordinate system to do this in?
That's a circular path. So
Yeah.
maybe polar.
Yeah, so this looks like something, this looks like a single polar variable. To draw specifically exactly what that is so 0 to infinity along the x and the y axes is essentially I'm integrating over this quadrant 1, right? X is always positive and y is always positive, and I have a little piece of this, and this is dA is equal to dx dy of this function, right? So the values of the function in the first quadrant. Is there any reason I would want to do that in the hardest coordinate system possible for that particular problem? Probably not. I could do that in polar coordinates instead. And as long as I'm integrating this, which goes from theta equals 0 to theta equals pi over 2. That's what the first quadrant is. And I'm using the correct piece of area. So here dA is equal to, we've been through this a million times, rho d theta d rho. Right, so that's got the correct units of area. I'll do that instead. So changing to polar coordinates. So it's really 2D. Alpha squared is equal to integral, and we'll just say first quadrant and fill that in a second. So it's an area. E to the minus rho squared, and then rho d phi d rho. I think we've been using phi a lot, but I just writing it as theta. Theta is fine. So integral d theta d rho. Okay, the magic trick, and this is something that you either have seen this, you're not expected to be inspired every time you find an integral like this. The magic trick, what have we done here that makes life easy and tractable now? We have rho to the first power downstairs, so we can actually take the antiderivative of e to the thingy squared. So now we can actually take this integral, right? Because we have rho down there. And writing in the limits, so we go from 0 to infinity and 0 to pi over 2, rho e to the minus rho squared, d theta d rho. Okay, the theta, there's nothing interesting with respect to theta, so that just gives us a pi over 2. And then 0 to infinity, now something that we can actually do. Because we have the derivative of the thing in the exponentials argument upstairs. And then that equals 1/2, because we get a negative 1/2. So minus. So we get a minus 1/2, and then the 0 goes away. The 0 is negative 1, so that's minus minus pi over 2 times 1/2, so that equals pi over 4. Which means that alpha itself, this integral, is root pi over 2. So that's when you look up the normal distribution, which is, this is kind of the active ingredient in the normal distribution. There's a pi over 2 out in front to normalize it. Okay, so that was a whole lot of work. Getting back to our original integral, so we did this change of variables, or u sub. So we ended up with gamma of 1/2 is equal to, after substitution, this. But this whole thing is alpha. So we have root pi. Okay. Next time somebody stops you on the street and asks you what 1/2 factorial is, the answer, of course, is the square root of pi. So now tell me what gamma of negative 1/2 is equal, and tell me what gamma of negative 3/2 is equal. And we'll make sure you got that, and then turns out, lo and behold, Mathematica actually has the answers of this.
Gamma negative 1/2 would be negative 1/2 root pi.
So that would be, I think you got to flip the thing. So this is minus 1/2. Yeah.
Got it.
Is gamma of 1/2. So the minus 2 goes on the other side, but yeah, right idea. So minus 2 times, so it's the negative inverse of the thing, or just inverse of the thing. So minus 2 times root pi. Minus 1/2 factorial is negative 2 times the square root of pi. Super crazy. And then how would I get negative 3 factorial? So the easy way of saying it is when you're going up with factorial, if I'm getting 4 factorial from 3 factorial, I multiply by 4. If I'm getting 5 factorial from 4 factorial, I multiply. Here we're going down, so we divide. So minus 2/3 times gamma of minus 1/2, which is equal to minus 2/3 times minus 2 times the square root of pi is 4/3 root pi is minus 3/2. Gamma function of minus 3/2 factorial. Oh, sorry, I wrote one wrong thing. So this is gamma function of minus, so this is gamma function 1/2. Remember the z minus 1, so this is actually minus 1/2 factorial. I think everything else is okay. Okay, I will, before we show how to work through this on Mathematica, which is just typing gamma, to be honest, let me write down one important thing that we've done enough work, we will not prove. And you'll see why this is really useful. So this inversion formula basically lets you flip from positive to negative values. So this is a pi. So this reflection formula essentially comes from the same sort of integral and work that we did to get gamma of 1/2. What this actually tells you as well, which is why second reason it's important, is not using it, but just kind of understanding its properties, is what happens for z in, I don't know what the most elegant way of writing this. So pi is just a number, but sine pi z blows up. Where does sine of pi z blow up? So sine of negative pi is 0, right? Sine of negative 2 pi. So when z is equal to a negative integer value, oops. We have a problem, right? So one or the other of these is going to blow up. So either gamma of z doesn't exist or gamma of 1 minus z doesn't exist. And these are what are called poles, if you know a bit about complex analysis. Okay. Okay, let's see if Mathematica recognizes our insanity. What is gamma of 1/2 square root of pi? What is gamma of minus 1/2 minus 2 times square root of pi? What is gamma of minus 3/2 4 root pi over 3? Good. And then let's see if we can actually try that formula, see how the reflection formula would work. So just in comments, what the reflection formula says is gamma of z times gamma of 1 minus z is pi divided by sine pi times z. So this would mean that gamma of minus 3/2, 1 minus gamma of, well, actually, let's just use our original examples because we know what those are. Gamma of minus 1/2 and we might have to simplify this, minus 2 pi. So that's pi looks kosher. And then pi times 1/2. What if I missed a 2 on this or something? Oh, I see. So I'm not doing what I'm saying I'm doing. Yeah, that makes sense. So 1/2 minus 1/2 is that. So yeah, that's sensible. Yeah, it's not the formula that's wrong. It's my ability to subtract by 1. Okay, so let's do this for something interesting then. Let's do 1/4, and then 1 minus 1/4 would be 3/4. And then I want to simplify. Okay, so something pi divided by something that's less than 1 is about right. So that is the reflection formula. Any questions about anything that we've covered so far? So I would actually crack open Mathematica and mess around with some of these plots. Specifically what the complex plot that I showed you guys is the argument of a complex valued function.